it. So, shh.
I want to get one of these. Fan the air.
Oh my God. All right. Shh. So, we're starting the radicals unit, so we first need to discuss roots. We already talked about your perfect squares and your perfect cubes. Those are things, like I said before, if you have those first 25 perfect squares memorized and those first 10 perfect cubes memorized, it makes this unit a little bit easier because what you're going to be doing is you're not working with perfect ones. You're going to be working with irrational numbers. And irrational numbers, when you try to take the square root of it, there is not a perfect value, meaning there is no finite value that will make it a perfect square. Okay, so like 64, that's a perfect square because its square root is 8. But 63 is not, because 63 doesn't have a single value that when you multiply it by itself will equal 63. I will call you out in the middle of the video and I will send it to your parents. Now, first thing that you need to understand when we're talking about radicals, the reason that they're called radicals is because of this symbol right here. This is called our radical sign. It's a square root sign, but we do call it the radical because it's not just representative of a square root. The only time that it's representative of a square root is if it's got this written with no numbers attached. If you have a little number in the corner up the left, that number will indicate what type of root you're taking. So if there's a little 3 there, what would look almost like an exponent but it's in the front of it instead of in the back, that would mean that it's a cubed root. So that means that you've got a base times itself to equal whatever number's inside. You can have a 4th root, a 5th root, a 6th root, and so on and so forth. Basically, your roots, they are exponents. A square root just means it's an exponent of a half. So you can have fractional exponents. 1/2 is just a square root. An exponent of 1/3 is a cubed root, and so on and so forth. Okay? So again, this is called our radical sign. So we've already know that if we take a root of a value, square root of 100. Now technically, a square root, you guys learned it, it's going to be equal to what? 10. But technically, it's a positive and also a negative 10. Because 10 times 10 is going to give you 100, but negative 10 times negative 10 is also going to give you a 100. So whenever we take square roots of values, a square root of a value could be a positive and it also could be a negative. So when you're indicating the answer, you should put a plus and a minus sign in front of it to indicate that it has 2 roots. Now, sometimes they will indicate that they only want the positive root. Sometimes they'll indicate that they only want the negative root. Okay? So if I happen to have a negative sign in front of it, it means that I only want the negative root. Okay? Now, even though you didn't learn about 1.21, you did learn about 121. What was the square root of 121, Jordan? 11. So what do you think the square root of 1.21 is going to be, Annie? Very good, 1.1. So this would be both positive or negative 1.1. Okay, if I wanted the negative square root of 25, what would that equal? The negative square root of 25. Heaven? Just negative 5. Okay, so these again, those are values that you should have memorized. Now, if I were to throw in a fractional value, if I have the square root of 36 over 169, this can actually be broken up into numerators and denominators. Now again, you do not need calculators for this part because you should have this memorized. But you can break this up to where you're just trying to identify the square root of 36 over the square root of 169. So who can raise their hand and tell us what is the square root of 36? Mateo? 6. Good. And what is the square root of 169? Miles? 13. So you get 6 over 13. That is as simplified as it's going to get. That is your final answer. Now, we also have situations in which, again, it's not a perfect square. So like square root of 30. It's not perfect. And eventually, I'm going to teach you guys how to simplify non-perfect squares in a different manner. But at this moment, we're just going to go ahead and estimate them. So if they're not perfect, we're going to estimate it. So the manner in which you estimate a perfect square, you first have to identify the two perfect squares that it falls between. So you're going to want to find the two perfect squares that it falls between. So what perfect square is smaller, like the next direct perfect square that's smaller than 30? Annie? Huh? The perfect square, the value. 25. So 25, even though there's other numbers that are perfect that are smaller than that, like 16 and 9, the next direct square, perfect square that's smaller than 30 is 25. Okay, so we know that it's going to fall between a square root of 25 and then what is the next direct perfect square that it's larger than? That's larger than 30. Chelsea? 36. So we've got the square root of 25 and the square root of 36 that the square root of 30 is going to fall between. So now we just have to find out which one is it closer to. So how far apart? What is the gap that is between 25 and 30? 5, right? It has a gap of 5. And what is the gap between 30 and 36? 6. So this is a gap of 6. So it's closer to the square root of 25. So that means that the square root of 30 is approximately 5. Again, it's just an estimate. So I'm going to give you guys a couple little practice problems to try on your own. All right, go ahead and do those 3 on your own. All right, who can tell me what is the square root of 225 over 625 going to give us? Mateo? And you gotta simplify it. Three-fifths, very good. Okay, so the first thing that we would do is we would split it up. So we know that we are going to take the square root of 225, which is going to be equal to 15, and then the square root of 625, which is equal to 25, but then you have to simplify it. They're both divisible by 5, so that would give us 3 over 5 as our simplified value. Okay, what about for problem number 7? Oh, and don't forget that it is plus or minus. It is plus or minus. Okay, what about for problem number 7? What is that going to give us? Kendall? Plus or minus 20. Don't forget your plus or minus. Okay? Because remember, it could be positive, it also could be negative. So it could be a plus or a minus 20. Okay, and then for problem number 8, square root of 54. Elijah? About 7. So you have to say about, so it's about, and I should put plus or minus. It's about plus or minus 7, okay? So remember the two square roots that this falls between. It falls between the square root of 49, and it also falls between the square root of 64. It happens to be closer to the square root of 49, so it is approximately a plus or a minus 7. Okay, any questions? All right, let's go on then and talking about the cubed roots. Same idea with the cubed root. So for a cubed root, again, it has that radical sign, but it's going to have the little 3 up in the corner. That indicates that you're taking a cubed value from it. Now with the cubed root, you don't have plus or minus an answer, because if you're taking the square root of a positive value, then you have to get a positive root as your answer. Okay, because you can't do a negative times a negative times a negative to equal a positive. So whenever you're taking the roots, if it happens to be an odd number root, you can have a negative inside the radical. So you can have a radicand that is a negative value. If it's an even number root, so like square roots, you cannot have a square root of a negative number. You eventually will learn about how to do square roots of negatives. Those are called imaginary numbers. So they're values of I. Right now we're working with real numbers. Okay? So here, if we have the cubed root of 125, who remembers what was the cubed root of 125? Annie? 5, right? Because 5 times 5 times 5 will give us 125. And it has to be positive. It cannot be negative. Now, if I wanted the cubed root of negative 64, what would that have to equal? Mateo? Huh? But if I wanted it to be a negative 64, negative 4. Okay. Same idea if it's a fractional value, and then you have a 216 over 343, and you wanted the cubed root of it. You would again split it up. So we would want the cubed root of 216, and we would put it over the cubed root of 343. So what's the cubed root of 216? Annie? 6. What's the cubed root of 343, Grant? 7. So you would have 6 over 7 for the final answer. Okay, so it's the same idea that you would follow with the square roots. The only difference is that when you take a square root of that value, it can be positive and it can also be negative. But with a cubed root, it's very specific. It has to either be positive, or if it's negative inside, then it would have to be negative for your answer. Okay? If you come across a problem in which we give you an equation and we ask you to solve an equation, so if I say, hey, the value of x squared is equal to 196, who can tell me what is the inverse operation of squaring a value? What do you think the inverse is going to be then? Doing the square root. Remember, we talked about this back in our geometry unit, that if we wanted to get the, like if we were given the area formula and we were told area equals this value, you need to find out what the radius is. We knew we had to divide the area by pi, but then to get the radius, you had to take the square root, because the opposite of r squared is to take the square root of the value, and that would give you r itself. So it's the same thing for here. If we know x squared is equal to 196, then your inverse operation is going to be to do the square root. So the inverse of a power is the root. So the inverse of a square is a square root. The inverse of the cubed is a cubed root. Inverse of a power of 4 is a fourth root, and so on and so forth. So all you would have to do is take the square root of x to the second power and the square root of 196. So square root of x squared is just going to be x. And what is the square root of 196? Annie? 14. Now again, this can be plus or minus. Let's not forget that. It can be plus or minus 14. Okay, for number 5, if I give you x to the third power is equal to 8. X to the third power is equal to 8. What do we need to do to solve it? Lena? Put x to the third power inside the cubed root. So you're taking the cubed root of both sides. So your inverse operation in this case is to do a cubed root of both sides. Okay, so we're going to take the cubed root of x to the third power and a cubed root of 8. So the cubed root of x to the third is just x. And what's the cubed root of 8? 2. And in this case, it will only be positive because you cannot have a negative that will equal positive 8. Okay, because negative 2 times negative 2 times negative 2 would equal negative 8. So it has to be a positive 2. Any questions so far? Am I going too fast, or?
No.
You guys are okay? All right, good. Because this is the easy stuff. Yeah. This is the easy stuff. That wasn't a joke. That was serious. All right. So before, like I told you guys, we're working with real numbers. Like I said, there is no such thing like a negative square root of 16 is not the same thing as a square root of negative 16. Those are not the same. Okay, the square root of negative, or the negative square root of 16, that's going to be equal to a negative 4. But the square root of a negative 16 is going to be your imaginary numbers. So it's actually going to be equal to what's called 4i. Those are imaginary numbers. And you'll get into that when you guys get into high school. But I think imaginary numbers are really, really simple. Basically the idea, so I'll just tell you the idea of it. For imaginary numbers, the value of I represents the square root of negative 1. I to the second power is actually equal to a negative 1. I to the third power is equal to the negative square root of negative 1. And I to the fourth power is equal to the value of positive 1. And so when you're working in imaginary value numbers, every single value can be rewritten as a coefficient value or a root value with an I value attached. But again, you're not going to get into that stuff until you get into high school. It's very, very simple. And then it just keeps repeating, like I to the 5th power would be a square root of -1, and I to the 6th power would be -1, and so on and so forth. It just keeps repeating that same process over and over and over again. Okay? It's not weird, it's imaginary. Okay, so like I said before, we are in real numbers, and real numbers can be split up into basically 2 large units, your rational values and your irrational values. What we're going to be working with right now is the irrational values. So you've got this large chart that represents the set of all real numbers. So these are all your real numbers. And you have 2 gigantic sections. This first section is the section that we've always worked with. Those are our rationals. Okay, and rational numbers are things like our fractions, like 1/2, decimal numbers, 0.25. Decimal numbers that can actually repeat, so 0.7 repeated. Fractional values that when you change them into decimals, they're repeated, so 2/3 or maybe even -2/3. Okay, those are considered to be our rational numbers. And inside of the rational numbers, you also have other subunits. So inside of the rational numbers, you've got what we call our integers. Okay, so our integers are all of our negatives and our positive numbers. So we've got -3, -7, +2. All of those are considered to be whole number positive or negative values. Those are called our integers. Okay, and inside of the integers unit, you've got your whole numbers.
Is that -2 at the bottom?
+2. So inside of integers, you've got all of your positive numbers, which is like 2 and 10. And then inside of whole numbers, you even have naturals. Naturals was where it's just 2 or a 1 and larger, just 1 and larger. Whole numbers would include your 0. Natural numbers is just 1 and up, all wholes.
Could a whole number be like -5?
A whole number cannot be negative, but integers can. Integers can be both positive and negative wholes. Rational numbers can be both positive and negative whole numbers and fractional values and decimal values, as long as the decimals repeat or terminate. Okay? So that's why every whole number is also called a rational number. Every integer is also called a rational number. But not every single rational number is called an integer or called a whole. It's kind of like with your hand, and I hate using this example because there's always a kid who wants to argue. Every single pinky is a finger, but not every single finger is a pinky. Okay? Every single pointer is a finger, but not every single finger is a pointer, right? So you've got subcategories for what you call your fingers. You've got your thumb, you've got your pointer or ring fingers, you've got your pinkies, but you don't call every single one of them a pinky. You don't call every single one of them a thumb, but they all together are called fingers. Shh. It's the same thing here. Every single number in this set, every whole value, negative value, fractional value, as long as it can terminate or repeat as a decimal, they're all called rationals, but not every rational number is called a whole number. Okay? You were going to say something?
Oh, yeah, I was joking.
Don't make a joke. Shh. Because jokes sometimes, guys, especially with this unit, the jokes can sometimes throw people off. So don't do it. Okay? Keep the joke to yourself. Then outside of the rationals, Still inside of the reals, we've got our irrational numbers. And there are no subgroups inside of the irrational numbers. You're either rational or you're irrational. Okay, irrational doesn't have anything inside of it. But these are the values that do not terminate, they do not repeat, they have no rationality to them. So values like pi. Okay, your non-perfect squares like the square root of 2. Okay, Isn't it what? Is 1 times 1 2? Yeah. All right. Just anything else, like if we have 1.68, 2, 3, 5, 1, 4, 2, 7, it just keeps going and going and going, and there's no pattern to it. There's no repetition. There's no sequence of it. Then that's an irrational number. It just keeps going on forever. Pi is an irrational number. We estimate pi. We estimate it to be 3.14, but the fractional value of pi is 22 over 7, and 22 over 7 is, it's irrational. It does not stop. It just keeps going. Jordan, did you have a question?
Oh, I was going to ask you
Okay.
Is pi?
Huh?
Is it just a number?
Pi is an irrational number.
Who made pi?
At 22 over 7, but we estimate it at 3.14 in order to be able to do simple calculations. But 22 over 7 is its most definitive value. Okay?
But what is it? Is it like something to do with circles?
It does have to do with circles. We just learned that unit, remember?
It can't just be a number with no reason in it.
Oh, honey, there's a lot of those that go around. And in math, when we don't understand something, we make something up and then prove it. All right, so what we're going to do is we're going to identify all the sets that certain numbers will belong to. You need to identify every single set that it could possibly belong to. So for example, if I have the value 0.2525525, and it keeps going on like this,
Irrational.
we obviously know, well, no, it's not irrational. It repeats. Because of the fact that it repeats, then that makes it a rational number. We definitely know that. But it's not a whole number. It doesn't have a whole number value to it. It's a decimal value. So that means it cannot be an integer, it cannot be a whole number. So it is a rational number, and all rational numbers are part of what set?
Real number.
Real numbers. So it is also a real number. It is a rational number, and it is a real number. Those are the sets that it belongs to.
Isn't every number a real number?
Except for the imaginary numbers. Aristaea's like, okay. All right. 0. That is, start with the very smallest. Is it a whole number? Yes. It is a whole number. So if it is a whole number, then it means it is also an integer. And if it's an integer, it is also a rational number. And if it's a rational number, it is also real. Okay, so shh. What about square root of 3? Irrational. Guys, stop talking. It is an irrational number. It is not a perfect square. If it's not a perfect square, there's nothing we can do about it. So it is an irrational number, but again, all irrational numbers are also real. What about the negative square root of 16? Shh. The negative square root of 16. Can that be a whole number?
No.
Why not?
Because it's imaginary.
What is the negative square root of 16?
-4.
Negative 4. Can negative 4 be a whole number? No. Shh. Your sub-conversations need to stop. Negative 4 is not a whole number. Whole numbers have to be all positive. But what can negative 4 be? An integer. So the square root of 16, that is an integer, because when you simplify that value, it's negative 4. And if it's an integer, it means it is also rational. And it is also real. So that's the identifying of what sets that it can belong to. Not every number is real. Remember, there are imaginary numbers. If it's got a negative inside of a square root, then that makes it imaginary. Okay? All right, so what we're going to do is I'm going to give you guys a homework sheet. It's going to practice utilizing your roots and your cubed roots, simplifying them down, categorizing your values into their sets. It's due tomorrow.